Hi, and welcome back to this video. Let's move on to the components of Hadoop. HDFS is a master-slave architecture where the name node acts as the master and the data nodes act as the slaves. Data nodes continuously communicate with the name node. Data nodes also have a secondary name node. Let's see about these individually. In brief, the name node manages the file system namespace, controls the read-write access to files, manages block replication, and checkpoints the namespace and journal namespace changes for reliability. Let's understand each of these functions at a more granular level, beginning with the managing file namespace. The HDFS namespace is a hierarchy of files and directories. Files and directories are represented on the name node by inodes. Inodes hold file metadata including regular file or directory file types and also hold the list of blocks that are pointers to the data, which in turn record attributes like permissions, modification, access times, namespace, and disk space quotas. The file content is split into large blocks, and each block of the file is independently replicated at multiple data nodes. The name node also controls the read-write access to files. An HDFS client wanting to read a file first contacts the name node for the locations of data blocks comprising the file. Then it reads the block contents from the data node closest to the client. When writing data, the client requests the name node to nominate a suite of 3 data nodes to host the block replicas. The client then writes data to the data nodes in a pipeline fashion. The name node manages the block replication. By default, it is 3, but this can be increased or decreased by simply changing the value in the configuration file. Now let's understand checkpointing namespace and journal namespace changes for reliability. HDFS keeps the entire namespace in RAM. The inode data and the list of blocks belonging to each file comprises the metadata of the name system. Persistent record means the information that is infrequently accessed and not likely to be modified. Persistent record of the metadata stored in the local host native file system is called a checkpoint. The name node also stores the modification log of the metadata called the journal in the local host's native file system. The locations of block replicas may change over time and are not part of the persistent checkpoint. Now let's discuss data nodes. Serve read-write requests from clients, performs replication tasks upon instruction by the name node, and reports block information and system state. Let's again understand this in a bit more detail. So coming to the first function of the data node, the client contacts the name node to access or write a file to the file system. The name node has all the information about the data nodes, like where are the file blocks stored and how much resources are free on the data nodes. And the name node tries to provide the information of the blocks that are closest to the client. Data nodes perform replication of blocks across the cluster. So the same data block is replicated across multiple nodes in the cluster so that the system is fault tolerant. The next function is that data node reports block information and system state to the name node. During normal operation, data nodes send information, also called heartbeats, to the name node to confirm that the data node is operating and the block replicas it hosts are available. The default heartbeat interval is 3 seconds. If the name node does not receive a heartbeat from a data node in 10 minutes, the name node considers the data node to be out of service and the block replicas hosted by that data node to be unavailable. Now let's move on to understand the interaction between the various HDFS components. A client accesses the file system on behalf of the user by communicating with the name node and the data node. The client presents a file system similar to a POSIX, so the user does not need to know about the name node and data nodes to function. Let's see this with an example. Let's say a client wants to access the file and hence contacts the name node regarding the same. The name node acknowledges the client with the block IDs and the location of the data block stored across the cluster. The client then communicates with the data nodes, which on the instruction of the name node gets the required information. So here we see that data nodes are just the workhorses. and do whatever is told to them by the name node. The entire storage information of all the blocks is stored on the name node. Now, there is one question that comes to mind. What happens if the name node goes down? A very crucial question. Without the name node, the file system cannot be used. In fact, if the machine running the name node was obliterated, all the files in the file system would be lost, since there would be no way of knowing how to reconstruct the files from the blocks on the data nodes. For this reason, it is important to make the name node resilient to failure. So I hope you enjoyed this video and learned from it. In the next one, let's see how the name node can be made a little bit more resilient. I'll see you there. Thank you.